I'm Tom Ger, and I will be co-teaching this Fox 2020 tutorial on relaxed locally decodable codes together with Igor Shinkar. So before I'm going to tell you about what relaxed locally decodable codes are, I want to tell you why I'm so excited to tell you about them and why one might care about relaxed LDCs. So at least for my own personal experience, I got to know relaxed LDCs simply because they turned out to be the solution for problems that I was trying to solve for a long time. And it happened on numerous occasions that I was stuck for a very long time on a problem, and then I really hope that there is a tool that can help me, and the relaxed LDCs came to the help each time. So in this tutorial, we'll tell you a little bit about what is this notion, why is it useful. We'll show you how to construct locally decodable codes. We'll show you how to prove lower bounds, which show the limitations, and hopefully show you why they are useful and how you might be able to use them to solve problems in your own research. Okay, so without further ado, let's start. Okay, so we'll start with a quick review of coding theory. And I guess the beautiful thing about this format is that if you already know that and that just pulls you out of your mind, then just feel free to skip a few minutes ahead. Okay, so in coding theory, our goal is as following. We start with some unstructured information, this X here. And we want to encode it such that it would be robust to noise. So what I mean by that, we take this unstructured information and we endow it with symmetry and structure and nice properties that will allow us to tolerate error and still be able to recover the code. So of course, this comes as a price. So as you see, this C of X is indeed longer than this X. We introduce redundancy to get this robustness. And then we get some adversarial noise. So you can think about all of these red parts here as corruptions. You can think about this like bit flips, for example. And the point is that we're getting a corrupt code word, which is hopefully not too corrupt. And as long as we have a certain bound on the amount of errors that we have, we can decode it into a string X. Now, a little bit more formally, we'll say that an error correcting code is a map which takes k bit strings and map them into n bit strings, where n is greater than k. And the key property that we'll care about is that for every two messages, which are different, X and Y, these two code words will be far apart. So for example, if here we had this X and Y, which are close to each other, they will be mapped into code words which are very far from one another. And we have two parameters that we care about, main parameters. One of them would be the distance of the code word, which is the guarantee, this delta that will tell us how far these two code words are. And the other one would be rate, which is simply k divided by n. This is a measure of the amount of redundancy that the code incurs. So the name of the game is typically to get the best possible distance delta while getting a rate which is as small as possible. Okay. So now, what are locally decodable codes? Well, locally decodable codes are error correcting codes, as we saw before, but one that admit this beautiful local to global phenomenon. So what do I mean by that? Suppose that we have this massive code word. Think about perhaps a huge email server where you have tons of data. And we only want to recover one bit of information or one symbol. It might be an email message, or it might be just a single bit. But suppose that we only want to recover this one bit. So in this case, reading the entire massive dataset could be completely impractical, and we want to do it locally. Of course, in complexity theory and various settings in algorithms, we have many other different reasons why we'd like to probe an object locally. And this is the idea in locally decodable code. So we have a decoder. The decoder gets as explicit input an index, which is which position we want to decode. This is I. And it outputs, so what it does, it make a small number of queries, hopefully of one or as small as possible. And then it outputs the message bit, which lies in the ith place, right? Or we can be a bit more formal here. So we have this code. In our setting, we restrict our attention to codes which are binary. And we say that our code is an LDC if we are given some string, and we say that this string is delta zero close to be in the code word, delta zero close in Hamming distance. And we often will call this delta zero the decoding radius. So as long as we are within the decoding radius, that as long as W is not too corrupted, then the moment for every index that we would like to recover, we can make these Q queries and then return the correctly decode the ith bit with probability 2/3. These are locally decodable codes. They were introduced by Katz and Trevisan 2 decades ago. And in fact, even before Katz and Trevisan, who introduced the systematic study of these codes are so fundamentally important, these local to global properties that they admit, that they were actually being implicitly used in the literature, in the PCP literature, in other different settings, where one wants to make this type of decoding, which is local. Okay, so these are locally decodable codes, and it's an immensely important notion. And just to give a bit of an example before we go into details, I want to show you how does an LDC look like. Maybe one of the most simple examples that one can think of. And specifically, we'll be talking about the Reed-Muller code, and we'll instantiate it in 2 dimensions because, well, it's easiest to show, and my drawing skills are very limited. So what is the idea here? We have our input X. This is our message that we want to encode. And we'll do a 2-step process in order to encode it. So first of all, we'll take X and write it down as this 2-dimensional matrix, just like arrange the message in a grid. And then, so one way of thinking about it is just like writing it as a function, taking square root k times square root k into 0, 1, and it maps it in the natural way. So, if we want to recover the first bit, then this would correspond to F00. And if we want to recover the second bit, that would correspond to F01 and so forth. Now, what we want to do is to take the unique low degree polynomial, this is this guy here, which is a polynomial of the minimal degree that we can find, such that we can still have the condition that on this regime here, so when we are on X, it would coincide with the function f. Right? So an alternative way, we just stack our information here in X, and then we take a polynomial which is defined over a much larger finite field FQ, and it defines in the way so that it takes the same values on the location within this X, but otherwise this determines an entire, like this part here. So it determines all of the values here. And now, we have the Schwarz-Trippel lemma, and by that it tells us that if you take any 2 such low degree polynomials, they would be very far from one another. So this is why we have distance, and in turn, why this is a code, in fact. And now this is already where we can see local decoding because of the following observation. How can we locally decode if we're getting? So suppose we have this code word and this red smears are corruption, points that got lost. Now, we want to decode this position J here. So how do we do that? So the point is we use two important properties of low degree polynomials of the Reed-Muller code. So what we'll do is we'll take this yellow line, random line, which goes to J, and we will read the entire line and interpolate the value of J after we read the entire line. So what is happening? First of all, assuming this works, it means that we're only reading square root of K because the size of this line is only square root of K coordinates. So it's something which is sublinear in the size of the entire input. But the point, and because another thing is because like this line is samples C of X very well, we take a random line to this point and the random line can touch all of the various points. So with high probability, we will kind of duck and avoid most of the red points, most of the errors. And the last property is, and this is perhaps the magic of Reed-Muller, is that each one of these lines, when we restrict our attention just to it, it's actually a univariate low degree polynomial. And so this is also an error correcting code. And therefore we can just read the entire thing. Now it's not a local error correcting code, but it is an object with distance. And so we can read the entire thing and tolerate a small number of errors. And in some sense, this is something which is quite magical about polynomials. And perhaps this is why we keep seeing them all of the time. It's because they have this amazing property that I kind of can't stop appreciating. I think I heard it for the first time from Oded Goldreich. So the point is that if you take some, I don't know, m-dimensional low degree polynomial, and so this is an object, like a low degree n-dimensional polynomial. This is an invariant polynomial, sorry, that's a code. But not only that is a code, if you take any line and restrict your attention to this line, this is also a code. But this doesn't stop here. You can also take maybe a curve of dimension of degree 2, degree 3. You can take like higher and higher degrees, and all of these all of these curves would still be codes. You can also take planes, 2-dimensional planes and 3-dimensional hyperspaces, and all of these objects, like so many of them, would still be error correcting code. So in some sense, polynomials have this amazing property, and I'm not aware of any other object which has this property, that there exists a very, very large number of subsets of the code which are codes themselves. We might have a little bit of this phenomenon in a restricted amount in tensor codes, but nothing as even remotely as we have with the Reed-Muller code, low degree polynomials. Okay. So hopefully that was a convincing example. And I just want to very briefly mention some applications of LDCs just because they're important. And I want to make this point. But instead of going through all of these things, reading them out loud, I will just highlight a few of them, and you can, in the meanwhile, glance. So LDCs are extremely close to this theory of probabilistically checkable proofs, and we use them in that sense all the time. We keep seeing a very close relation with private information retrieval, where it's the situation where one wants to get a certain information from a database without revealing which location we've looked at. We also see it all around complexity theory and in property testing. We see it in various types of sublinear time algorithms. somehow, whenever you have sublinear time phenomena or sublinear complexity phenomenon, like in communication complexity, where you care about small amount of communication, with streaming algorithms, where you care about small amount of space, these codes keep appearing. And also, they're actually quite useful in practice. So Microsoft is famous for using them in variants such as locally recoverable codes in their Azure platform. In general, they are very important for distributed data storage. And this type of PCP techniques, which rely on DCs, have been proved quite useful for cryptocurrencies and blockchains. And who knows, perhaps the better LDCs that we'll have and the less redundancy that they will require, maybe we'll see more and more applications of them also in practice. Okay, so now this so far everything sounds all great and amazing, but there is a cost to this locality that we want, and the cost is that if we want to get this code with this amazing property that we can just query O(1) coordinates in order to recover a location, then we actually have to pay a whole lot in the redundancy that this code introduces. And in fact, for a very long time, it was thought that the best we can do is exponential length encoding. This is the Hadamard code, where you essentially take a message and you replace it by its encoding by every linear function. But then after a beautiful result by Kanin and Fomenko, in 2 steps, we actually found that we can use sub-exponential, but still super polynomial block length. So just to give perspective, when in many scenarios, not only that we want to have polynomial lengths, we typically want to have something which is linear or nearly linear block length. Otherwise, the redundancy might be too much. And to put this in context with respect to the limitation that we know, it's quite surprising, but because the best lower bound that we know is actually a very, very weak one. So while the best construction achieves something which is super polynomial in length, exponential, the lower bound is in fact nearly linear. So if we allow ourselves O(1) queries, then we get this here, the block length is n is k to the 1 minus 1 over k plus 1. So you take k bits and you encode it into k plus 1 plus a small constant, which is quite very weak with respect to the upper bound. Okay. As a side remark, if you care about locally correctable codes, which are codes in which instead of decoding a bit of the message, you can correct a bit of the code word, then their situation is even worse. You actually need exponential amount of redundancy in order to get this O(1) locality. And we've been studying these important notions for 20 years, and despite all of these applications that we get with the ridiculously large block length, after 20 years of studies, we still can get polynomial length, and let alone this nearly linear length, which we desire for many other applications. So what do we do? Okay, so what are relaxed locally decodable codes? So there is a rather modest relaxation. So what we do is we allow the decoder to abort, and by that I mean output an I don't know symbol, in this case bot, on a very small number of the locations. So this essentially means that we still have the same decoder and still gets this input decoding I and a corrupted code word within a certain decoding radius. But now the point is, rather than being able to successfully decode, we want it to either correctly output the value xi or say, I don't know. Now, of course, we don't want it to always say, I don't know. In that case, that would be completely meaningless. And so the condition tells us that on a very, very arbitrary large fractions of the coordinates, we will never say no. So being a bit more formal, we say that relaxed locally decodable code is some code. And here we might, just for convenience, we say that this is binary code, but it doesn't have to be. And it's a relaxed LDC. If we have this decoder, it gets a string and some input, which is delta 0 close. And on an input I, it makes Q queries. And what happens is the following things. So first is the condition that we mentioned before. So with probability, let's say 2/3, we will return either xi or bot. And then the second condition that we'll ask for, which is a non-triviality condition, is that if we're getting a perfectly valid code word, then we will not reject. And this is something very natural to ask. So we might, so on a perfectly valid code word, we'll just return the right value with probability 2/3. And the nice thing about it is if you have both 1 and 2 simultaneously, then by a well-known transformation, this also implies the other condition, which means that you will not reject on most occasions, 90% or however high you want it to be. So that's relaxed locally decodable codes. It's a notion that was raised by Ben Sasson, Goldreich, Hersha, Sudan, Vadan, in the same paper that introduced the notion of PCPs of proximity, which, as you will see, will be a very closely related notion that we shall use in upper bounds and constructions. And just to say one last point regarding what I mean by don't abort on 99% of the coordinate, what I really mean by that is that there exists a set of coordinates, let's say, you know, something which looks like this, of like 90%. Such, okay, and the point is that for every corrupted code word, there exists such a subset on which we will not abort. But the point is that we don't know this subset a priori. So that's the third condition. Okay, good. And so what do we know about relaxed LDCs? This is quite cool because this is quite a seemingly modest relaxation. We're not requiring something too much. But it opens a door to all of the strong techniques that we have from the PCP literature. And quite remarkably, it turns out that if we allow this relaxation, then not only we're improving from sub-exponential length or so forth, but rather we get a constant query at RLDC with a nearly linear length. And what do I mean by nearly linear? It means that I'm mapping k bits strings into n bit strings, where n is k of 1.001 or any arbitrary small constant epsilon that we will want. And in fact, we can actually do much more than that. We can get not more efficiency, but like we can get like some stronger properties. We can get a code which is a linear code, and it's not only relaxed locally decodable, it's also locally testable, which means that we can distinguish whether a code word is valid or far from valid. And we have linear distance, and we can have a trade-off of Q queries and block lengths, which is almost the best that you can expect because we also have some nearly matching lower bounds. So we have pretty excellent constructions. And in fact, in the next lecture, Igor will tell you all about how to construct the state of the art of these RDCs. And I just want to briefly mention that many of the applications that we have for locally decodable codes can actually be used with relaxed LDCs. And then they carry on and also admit some new things which are completely rendered impossible or intractable because of the sub-exponential length of O of 1 queries LDCs. And again, rather than listing them, I want to tell you about a paradigm which I think it's extremely powerful with relaxed LDCs. Because we can get this testability and relaxed decodability, it could be a replacement for the read Muller code, where we have constant locality. Whereas typically one has to work, if we parameterize read Muller in the correct way, we would still be with super constant query complexity. So whenever you see a situation where one uses read Muller code, which is quite a common thing, you can see it in so many different fields, then this is a very obvious go-to tool. Okay, and before we go to the rest of the lectures and before Igor shows you the most complicated example, I want to show you a very basic construction of relaxed LDCs, just to give a hint and taste of the result, and I would only very briefly mention how it works. So this construction, it's an example taken from the first paper which introduced this notion, and it's a relaxed LDC with slightly more than quadratic block length and constant query complexity. Now, the idea is very simple. What we want to do is we want to have a code word. So we're starting with some code, like some good error correcting code with maybe, I don't know, constant distance and constant rate, but no locality properties whatsoever. This would be this C of X that you see there. And we construct a larger code word that consists of 3 parts, each one of them serving a completely different purpose. So the first part is just the message being explicitly written. And the goal and the intention of that is that it's extremely easy to decode if it's not corrupted. So amazing locality. And then we have the second part, which is a code with good distance. So this is the same C of X, and the responsibility of C of X in this component is to provide distance, because we have one part which is very local, but has no distance at all. This is the X. And this is a part which has good distance, but no locality. Now, how do we merge this thing? I mean, ideally, I'd like to say, as long as these two are consistent with each other, then, well, I'm getting my distance from C of X, and then if I want to decode, I just query X. However, it might be the case that I have this completely corrupted X and encoding C of a completely different Y, and so this means nothing. So instead, what we have is a PCP of proximity oracle for each one of the decoding, for each one of the bits of the message. And what will this PCP tell us? The PCP will tell us that the code word is consistent with a message that decodes to a certain bit. So what do I mean by that? How would the decoder look like? We'll start by explicitly reading xi at a certain point. And after we read this xi, we know whether we have a candidate for decoding, 0 or 1. And then we will invoke the PCPI, which corresponds to this xi. And suppose that we got the bit equals to b. And the PCP will tell us whether whatever is written here in the code word part is a code word whose message decodes on the ith bit to the value b. So it tells us that this is a code word that is consistent with the value that we read. And so what we can do is we can output, so we run this PCP. If the PCP accepts, then we know that with high probability, the bit that was written explicitly here in X was correct. And if not, then maybe something went wrong, and in which case we output bot. And just two quick remarks regarding that. The first remark is PCPPs typically have lengths which is slightly larger than the statement. If you take the state of the art, like building on Ben-Sasson Sudan and Dino, then we can map statement of size n to statement of size n polylog n. So each one of these PCPPs is longer than the code word, and we actually have k of them. So this is quadratically larger, roughly, than C of x, which means that we don't really have distance. And this is precisely why you see these weird squares that I drew around C, which means that we duplicate C of x and we just write it like time after time after time after time until it takes a large portion of the code word, and this is how we get the distance. As for the second point, notice that in this case, whenever the PCPP reject, we are outputting bot. And so one may ask, so it suffices that we corrupt just a single coordinate, and then we'll say like always bot. So what prevents it from happening? So the point is that notice that if everything is completely correct, then the PCPPs will always accept, and we will know how to decode correctly. And then we can apply the transformation from BGHSV, which tells us that we have this like perfect completeness. By that I mean that given a valid code word, we always succeed, never output bot, and we have the other condition given by the decoder, and so we can get that on transformation with a new code with roughly the same parameters that would only output bot on, say, 1%. Okay. And just to conclude this introduction, let me briefly tell you about what's about to happen. So the next lecture, which Igor will teach, will tell us about the state-of-the-art construction of relaxed LDCs. And this is a beautiful construction which builds on at least 5 or 6 previous works, and it involves tensor structure and this nice algebraic structure of Reed-Muller code words and consistency test via random walks. It's quite a beautiful construction, and I think it's going to be very interesting. Then in part 2, I will show you a nearly tight rate, lower bound on the rate of such codes using a new and very nice techniques of relaxed sunflowers lemmas. And we'll conclude it by another video by Igor, where we mention some interesting open problems and directions and applications. So thank you, and stay tuned for the next